I'm going to go ahead and get started. I'm going to try to make this video pretty quick because basically it's just it's an overhead view of what Chapter 1 covers. The elements of design are, yes, I know this video is a little crooked. I will work on my video skills later. Whatever. The elements of design are ultimately, for a mechanical engineer, and this marker sucks, but you know what, I'm going to stick with it as long as I can. The elements of design are such that if you go to design something, you need to make sure that it not only does it work properly, but that it has some longevity, okay? So when you go to discuss design, you have to understand functionality, but you also have to understand preventing failure. Okay? You drive your car and all of a sudden your car breaks down, you're not going to be very happy with it. As an engineer, it's your job to design it so that it doesn't break down. You design a rocket that takes astronauts into space. You certainly don't want it to blow up on an international scale and show everyone how terrible of an engineer you are. It really speaks volumes about you, and it's just not good. So ultimately the elements of design are understanding the functionality, preventing failure, and working on quality. You want to have a quality device. And lastly, something that fits inside of constraints. Okay? When you go to design something, having a workable prototype, having something that actually does what you want it to do is ultimately the goal of everything. You want to make something functional. Now, the way that this course is going to be set up is that we are going to be discussing this first, and we're going to be moving into understanding functionality next. Talking about components that allow for different kinds of functionalities. Talks about different mechanisms that exist. Gives us different functionality. But overall, throughout the semester, we're going to be continuing to remember what is quality. What are constraints? What kind of constraints can you put on something? You know, it can't be too heavy. It can't be made out of a certain material. If you're going to be making a material that has to be food grade, you're probably going to be using stainless steel, copper, materials that actually work with food grade materials. You can't be using rusty iron. You can't do that. You can't cast iron something there. You will have constraints put on you based on what that specific component is going to be used for. And that's the reason why you go look up bearings, you'll find plastic bearings, you'll find oil-infused bearings, you'll find dry bearings, you'll find journal bearings, you'll find all these different kinds of bearings because every one of them serves a different purpose. Every one of them has its place based on the constraints needed for that specific component. So, as we talk about design, a really big component for us right off the bat is understanding what failure is. Okay, as a student, failure is when you don't get a good grade, or when you, maybe you don't do so well on the football team or something. Failure for an engineer means that, well, it means several things. First of all, it means a component breaks or cannot function properly anymore. Okay, if you have an elastic waistband in your pants and that elastic no longer is elastic, it has failed. It didn't break, but it's not performing the same function it has. If your phone or your computer is not booting up the operating system, your component has failed. It's not broken. There may not have been any leads necessarily broken, but it is unable to perform the function that is requested of it. And that is what failure is. It's an inability to perform. Okay? Now, causes of failure. This is fairly critical. A lot of what we deal with as mechanical engineers, both of the things I just mentioned, the elastic waistband, computer operating system, those are not really the realm of a mechanical engineer. That's a materials engineer, that's an electrical engineer. But what causes mechanical failure is usually excessive yielding of a component. You may have maybe a linkage bends in a certain way. If it bends in a certain way, it can't carry the same kind of loading that it used to. If you've ever used a car jack or something, if any of those components bend, they collapse almost immediately when any kind of pressure is put on them. So having any kind of yielding, it weakens a component. It may also cause it to jam, where now it is running into another component. So yielding is one. Fracture is another. This is probably the easiest to tell. If you have a component in an arm and all of a sudden it breaks in half, yeah, it's not going to be able to function properly anymore because it can't carry anything. It's broken. Okay. Other causes of failure. You may have fatigue loading, where now the connections are broken. You may have connections lost, where say you have a bearing fall out, and now it's grinding on an axle or something. There's tons of different causes of failures. This is really only a short list. This goes on and on and on. But failure is something that is fairly common. Everything fails. And a good designer has to understand what causes failure, because not only do we have to plan for it, we have to try to stop it from happening. Okay, if I'm designing two linkages that just bend up like this, maybe it's a hinge on a doorway, I need to understand where is this going to fail? How is this going to fail? What can I do as an engineer to prevent this from failing? And sometimes that means making a lot of assumptions. So as an engineer, you're going to end up making a lot of assumptions, informed decisions based on what you know the component is going to do. Now, sometimes the informed decisions that you make aren't accurate. They aren't right. Your component may break, but this is why verification, validation, and analysis is very necessary. You cannot design something and expect it to work perfectly because your assumptions were all correct. Quite frankly, oftentimes your assumptions are wrong. You have to put it in the situation. You have to put it through testing. You have to figure it out. This is why it's friggin' 2020, and we still have car manufacturers that are sitting down and doing million-mile car tests on their vehicles. It's not because they don't know how to make an engine. It's because they're validating that everything in that engine still works. And that's really critical. Okay, if a car manufacturer in 2020 with 120 plus years of design experience in automotive industry, if they still have to test their components, you have to test your components too. And you have to make sure they work. So the full design process for a mechanical engineer, if I were to just put this in a nutshell, full design process. Okay? Step one, you need to understand the functionality and the constraints. Okay? We talked a lot in all of my design classes about what are your functional requirements. What are your constraints? Okay? What is it that has to be a yes-no condition if your component doesn't have the functionality or does not follow the constraints, that component has failed. Okay? If it leaves particulates of metal in food, your component failed. Okay? This is ultimately the yes-no questions that have to be answered in order to begin the design process. Once you understand these, the next step is to understand measures of quality. Okay? What makes a good design? What makes a great design? What is most important to you? What is most important to your client? Hey, if weight doesn't matter, you can make it out of cast iron. If weight does matter, you're probably going to want to have some heavily reinforced, very specially designed components that are ribbed, that have sufficient reinforcement, they're non-linear components, that are probably made out of high-grade materials. Okay, if weight matters that much, you can cut weight, but instead of now just having a cast iron, big, bulky piece, now you have a very fine-tuned, difficult to manufacture, expensive component. Okay, that's your trade-offs. You've now picked cost. Well, cost and convenience and time has now been sacrificed for weight. In the aerospace industry, weight is critical. So in the aerospace industry, yes, they're going to pick this one over time, cost, and whatever that third one was that I said earlier. Okay? Measures of quality are ways by which you can analyze and compare different designs and different materials, different methods, different components, so that you can optimize and make a piece better. Okay? This ultimately gives you your conditions of what is better. This gives you your conditions of what is a satisfactory solution. This is what is a good solution. Once you understand these two, really, as an engineer, your next step then is to understand failure. Okay? Failure is when functionality is lost, or when your constraints are broken. What is going to cause that? Well, it's going to be your stresses. What kind of stresses are going to be carried here? Okay? Stresses, materials. If you're going to be using aluminum, you're going to be dealing with fatigue. If you're going to be using iron, you may be dealing with rust. If you're going to be using plastic, you're going to be dealing with fatigue, and you may be dealing with some yield stress. What is ultimately, what's going to be your material impact on what failure could be? Hey, once you understand failure, once you understand really the foundations of all this is really where you get into the design process. Okay? You understand what the requirements are, and then you design the piece to satisfy those requirements. This is kind of why design is a backwards process. You need to know what the component really does, what it looks like, how it's going to be evaluated before you actually do any design work. Once you've done your design work, this is where you step in validation. Okay? This is where you get in and you test the stresses, you test the longevity, you test the fatigue, you ultimately test your design. Does it work? Okay? So this is the design process that we're going to be using in this class. I am going to be giving you a semester-long project. My goal is to try to give it to you in class this week. Oh, excuse me, but there's no promises there. So I'm a busy man, and this has been a crazy week already. Just trying to get these lectures up. But I will give you a project for the semester, and you will have to do all 5 of these tasks, not excluding validation. You're going to have to test this. Okay, and we'll talk about all of these things. There will be a lot of discussion on each of these processes. If you have any questions, please let me know. Again, and some of you I will see in class tomorrow, Wednesday, and some of you I will see in class on Friday. If I don't have you scheduled to be in class either Wednesday or Friday, don't show up. I'm going to try to get you a homework assignment today. Focus on the homework assignment instead. Okay? All right, good talk.